This video is going to go through question 5 from the A2 November test. So it starts with a comparison between the delocalized model and the Kekulé model, and it asks you to explain experimental evidence that led to the development of the updated model, and then describe the bonding in the new one. So first of all, we've got the experimental evidence. You could have any two of the following three. So one, the carbon-carbon bond lengths are the same. In benzene. Now that rules out Kekulé's model. You could have had the enthalpy of hydrogenation is less exothermic in benzene. Or you could have benzene doesn't react with bromine. Anything to say that it's got a greater stability, but this is one of the examples that would be the case. Then, to go through the bonding in benzene, or the delocalized model, for 1 mark, you needed to say that p orbitals overlap to form a pi bond. And then these electrons, put in brackets pi, electrons are delocalized. You could have drawn a diagram to show that as well. But you got 2 marks for this, so any 2 of those, and then 1 mark for that, 1 mark for that. B, that's for the mechanism. So we've got in this mechanism 3 stages. The first is the generation of the electrophile. I'm going to use our catalyst, react it with chlorine. That's going to give me AlCl4- plus Cl+, which is our electrophile. Then, actual mechanism then for this reaction. Curly arrow from the ring to Cl+. This creates our intermediate, and you had to have this in the correct position. Actually, no, you didn't. It could have been anywhere. Oh, it does. No, it does tell you it's 4-chloro, so it does have to be on the 4th carbon. So we have a chlorine and a hydrogen. The ring's been broken, and we'll have a positive charge on it. Now, the curly arrow coming from the bond to the hydrogen back into the ring. And that has the H+ then breaking off, which gives us now our 4-chloromethylbenzene and a H+. And so in our third and final step, we'll have H+ reacting with our AlCl4- to regenerate our catalyst plus HCl. So that's 5 marks. 1 mark for this part, 1 mark really for each of these, and then 1 mark for that. In 5 parts C, we're going to look at directing groups. got CN first of all, reacting with chlorine, and we want to see where the chlorine will go into the benzene ring. If we have a look at the table, we see it's free directing. So if that's 1, that's 2, 3's here, so the chlorine's going to go on there. For NHCOCH3, when that reacts with Cl2, so you don't need a catalyst because this is quite reactive, it will either go to 2, and that is 1 monosubstituted product, and because it's monosubstituted, we couldn't draw the 4-chlorine on the same one. This is 2,4 directing. We couldn't do it on the same one. We had to draw another NHCOCH3 benzene group with a chlorine on. So 1 mark for that, 1 mark for that, 1 mark for that. Part 2 has our benzene ring, and it wants with tertiary amine at the top. We've got our benzene ring, and it's a tri-substitution, so we'll have 2, 4, and 6. Would you need you don't need free HCl as well, so that's fine just to have that product. So why does chlorine react much more readily with this than it would with benzene? We've got 3 points to make here. The first is that pair of electrons on the nitrogen we've got here, that's donated into the delocalized ring. So pair of electrons is, I'm going to use the term partially delocalized into the pi ring, or just the ring. Then that makes the ring more electron dense. So our electron density increases. That means that when chlorine comes close to it, Cl2 is then more polarized. It can shift the electrons within the chlorine to form a pole. And that's the 3 marks for 5C part 3. That is question 5.